Hey guys, so finally, this is one of my favorite topics. This is called related rates. So we are going to get into related rates problem. This is actually going to be day 4 and day 5. So I'm going to pause it when we are about 3 pages in for the day 4. It's really just going to kind of intro you into everything. Um, and then day 5, we're going to continue. Okay, so we want to get these. These are fun, but they're usually a little bit tough. So I've kind of broken it down into some pieces at the beginning to help. Okay, so when finding derivatives and related rates, do we use implicit or explicit? So here, you really want to know, you've got to pay attention. What are you taking the derivative with respect to? Okay? And that's going to be a goal here. And I'll let you answer the second ones. But usually we're taking it with respect to time, but not always. So pay attention. Okay, so first thing we need to know is when we're kind of doing something, what are the variables? And are these variables constant or are they changing? Okay, so that's what we really want to pay attention to. So if I look at this cylinder, what's the volume of a cylinder? Well, I know I'm going to take the area and multiply it by the height. So I have 1, 2, 3 variables going on. So V is our volume, R is our radius, and H is our height. And I want to know, as I start increasing this with sand, which is changing, which variables are changing, and which ones are staying constant. So the volume is getting more, like there's more and more volume. So this one is changing. The height is growing up. This one is changing. The radius, though, look, here's a radius, here's a radius. The radius is staying the same. It is a constant. So those are going to be important things that we need to know when we move forward. What are my variables? Are they constant or are they changing? Okay, so a ladder is sliding down a wall. This wall is making a 90-degree angle. So I have a couple options. I can call this, let's go ahead and call this A, B, C, and I'm going to call this angle theta. Okay, so here I have 2 things I can really think of that are going to be happening here. I can think of my Pythagorean theorem, and I can think of all my SOHCAHTOA. And so maybe I'll just say sine for this one, because we don't want to go through every single one. So sine of theta is opposite over hypotenuse. Okay, so as I look at this, what are my variables here? A is the wall, B is the ground, C is the ladder. And as that ladder is changing, right, it's like falling down, the wall height here is getting, I guess I should put wall height, okay, ground length maybe, okay, and ladder height, length, whatever you want to call it. I don't care. Okay, so as this is happening, I can see that the wall height is getting lower as that ladder is sliding down, so that is changing. The ground length is getting longer, that is changing. That one's a negative change, that one's a positive change. But the ladder, that is constant. The ladder isn't like shrinking up or pulling out, the ladder just stays and falls. So that ladder length is going to be constant. Okay, so here if I look at these, theta is the angle between like the ladder and the ground. A, we said, was that wall height. And C is the ladder length. So as that ladder again is falling, theta is getting smaller. It is changing. The wall height is also getting smaller and it is changing, but the ladder is still a constant. Both of those were a negative change. Okay, so this next one. The volume here, we take that pi r squared times the h, just like we did with a cylinder, but now we have to, since it's a cone, we divide it by 3, which I like to pull out the coefficient in front for when we do derivatives. Power rule. Okay, so here's my volume formula for this. There are my variables. Remember, pi is a number, not a variable. So I want you to tell me V is the volume, R is the radius, and go ahead and see if you can get these down yet. H is the height. So this is now filling up with water. So the volume isn't changing, that's a positive change. The radius is also changing now. It's getting bigger, it's a positive change. And the height is growing, it is also a positive change. So there were no constants here. Okay, the next thing we want to do is talk about what all of the variables are meaning with the derivatives. So we're going to be doing a lot of implicit. So here's a scenario. An ant crawls directly away from the base of a vertical pole, and that pole is 3 feet tall. And here's the little ant guy. The ant is crawling at a rate of 1 foot per minute. And he is increasing his distance, so that's a positive. Suppose that d is the distance from the ant to the base of the pole. That's this right here. And they called that d. So if this is the d, this was a rate. So this would be my d with respect to time. See the time? Okay, let's keep going. H is the distance from the ant to the top of the pole. So I'm going to call this now H. Differentiating both sides of the original equation. So let's talk about where this came from. If we can see, this is my a squared plus b squared equals c squared. Okay, and why did they go ahead and plug in the 3? See how they have h and d? Both of these are changing, but this guy is constant. The pole height stays exactly the same. So that's why they went ahead and plugged it in. Okay, but let's keep going. So they differentiated with respect to time here. And so they got 2h dh dt. This is just a number. The derivative of a number is 0. And then 2d dd dt. Assume that at a certain time that the ant is 4 feet away. So d would be 4. What are h and dh dt at that time, including units? Okay, so that's kind of like a prompt of what's going on. But let's answer these two questions. Which of the following represents the rate at which the ant is crawling away from the pole? So that's why we kind of always want to label what's going on here. So the rate at which the ant is crawling away from the pole is the dt. And which would you plug in the 4 to? If they went when the ant is 4 feet away from the base, you would plug it in to the d. Okay, so we got to kind of understand what all of these variables are representing. So I want you to look through here, and I want you to label which ones are going to be constant, which ones are going to be changing, and give them their label of what the variable is. So height of the pole, from what we just saw up here. So height of the pole is a constant, and that is 3. The rate that the ant is crawling. So that's the rate that this ant is crawling, and they told me it was a constant, dt. They said that that was crawling at a constant of 1. The distance from the ant to the base of the pole. That distance is changing. That was d. The distance from the ant to the top of the pole. That they told me was h, and that's going to be changing as the ant moves. And the rate at which h is changing with respect to time. That is going to be my dh dt. Okay? So, looking at these now, which of the following equations appropriately represents the scenario when the ant is 4 feet away from the base of the pole? So if you remember, they told me that this was a 3, and now they're saying when this is a 4. This is a right triangle, so what does that have to be if I have a 3, 4, 5? Okay, so we got to know those Pythagorean triples. So if I look at what they gave me from up here, 2h dh dt, so now I'm going to do 2 times h is 5, and then I don't know dh dt, and then plus 2 times the d, and they told me the d is 4, and then they also gave me the dd dt, so I can plug that in, but they didn't here. Would have been a 1. That is A. Okay? And then go ahead and solve. So we know that the only thing left to do is plug 1 in for here, and go solve for your dh dt. See if you get 0.8 feet per minute. Okay, so this is the last page we're going to do for day 4. We're going to kind of put it all together with a little bit of some basic ones, and then we'll do some tougher ones. So these are just my guidelines, okay? Draw pictures, identify like everything going on. Write the equation that you need. Substitute the constants into the equation before differentiating. Okay, so the constants go in before you take the derivative. That's super important. Then try to go manipulate the equation so that you only have 2 variables. Usually you will only have 2 variables, but sometimes you're going to have to use some tricks that we'll talk about. Then you can differentiate implicitly, usually with respect to time. Plug and chug and solve. Okay. A pebble is dropped into a calm pond, blunk, causing ripples to form in the form of concentric circles. So those should actually be more circular. Okay. The radius of the outer ripple is increasing. So if I see this radius, at a constant rate of 1 foot per second. So dr dt equals 1 foot per second. When the radius is 4, at what rate is the total area? Area of a circle is pi r squared. So they want to know at what rate is that area? That would be dA dt changing. So I kind of drew my picture, I labeled everything they gave me, and I have the equation. This equation only has two variables, so I can go ahead and differentiate with respect to time. Now I'm going to plug in everything that they have given me. Then I want to make sure I know how to label. So an area would be in feet squared, and time was in, I just lost it, seconds. So this would be my answer. And again, I got my labeling from looking what's area, that's in feet squared, what's time, that was in seconds. So I kind of correlated the labels with those for the labels. Okay, we're going to do one more together for day 4. A rangefinder tracks a hot air balloon rising straight up from a level field. And it is moving straight up. So maybe here's my little rangefinder. Okay. 500 feet from the lift-off point. So the rangefinder, it said, was 500 feet away. At the moment that the rangefinder's elevation is pi over 4, so I have this theta, and we want to know when theta is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising? Don't know. Give that a variable. Don't care what you want to call it. At that moment. So now they want to know, what is this dx dt? So I kind of have 3 things going on that I need an equation for. I have an angle, and I have the base here, and I have the height here. So what equation relates all of these 3 things? So it's one of the SOHCAHTOAs. So this one is the adjacent, so I know sine's out, and this one is the opposite, so I know cosine's out. We are in a tan situation. So tan of theta is opposite over adjacent. This is in 2 variables, so I can go ahead and take that derivative. Tan is secant squared. This is where everybody messes up. Don't forget implicit differentiation. You took the derivative of a theta with respect to time. And then remember that we have talked about this a lot. Rewrite as the power rule. The derivative is just 150, but you took the derivative of x with respect to time. So this is going on now. Okay? Okay, so they had told me that theta is pi over 4, so I'm going to go ahead and plug that in. They told me that d theta dt is 0.14, and I want to find dx dt. So secant of pi over 4 is 1 over cosine of pi over 4. So 1 over radical 2 over 2, and then flip it, 2 over radical 2, and then I need to square it, 4 over 2. So that will give me 2. So this is 2 times 0.14, and then multiply the 500 over is dx dt. And so this one would be, with my label, x was in feet, and time was in minutes. And if you want to simplify, feel free. That's 140 feet per minute, but you can leave it to what we just had. Okay, so that's where we're going to pause on day 4. Day 5, we're going to do some more of these. All right, good job.